So this is supposed to be review from a long time ago. So what is the coefficient of x to the n, or sorry, x to the 10 in the expansion of 1 plus x to the 35? Okay. Okay, I've got some answers coming in. They seem to be converging on two different values. Any last answers? So what we're using here, what I want you to be using here is the binomial theorem, right? So remember, 1 plus x to the n is equal to the sum k equals 0 up to n choose k, x to the k. So if I have n as 35, so if I kind of plug in 35 here, then this is like 35 choose k over all the k's. And so if you think about the coefficient of x to the 10, it's going to be 35 choose 10. Okay, so there's no negative ones in there or anything. It's just 35 choose 10. Okay, so yeah. So you've got to remember the binomial theorem. It's very, very, very important. Not just in this course, but if you go on to anything else in combinatorics or also other parts of mathematics, you need to know the binomial theorem. So cement this, like stitch this into your memory, yeah, as soon as you can. Okay. So the reason I mentioned the binomial theorem is that we're going to look at an interesting extension of the binomial theorem to cases where we're not dealing with integers anymore. So here's a weird question. And frankly, I even find this to be a weird question. So what's the coefficient of x to the 10? So before we did 1 plus x to the 35, what if I take 1 plus x to the 35.5? Or in other words, if you don't like decimals, 1 plus x to the 71 over 2, which seems like the answer is like the question doesn't make sense or something. But actually this question kind of does make sense. And so that's the sort of thing we're going to talk about right now. So this is kind of an extension of the binomial theorem to exponents which are not integers. And the way to make this make sense is to think about Taylor series. Remember this? This is in calculus. You must have seen this before. But I feel like people see this in calculus, but they don't really understand it, which is okay. But suppose I take f to be 1 plus x to the p, where p is not 0. It's just some real number which is non-zero. So do you remember Taylor expansion? It says that f of x is, yeah, go ahead. Was somebody wanting to say something? So what should I write as my first, or what should I write here? Anywhere. So it's something like you take f of 0 over 0 factorial x to the 0, f prime of 0, x to the, sorry, no, yeah, of 0, yeah, x to the 1 over 1 factorial, second derivative of f at 0. So here I'm doing, maybe it's called a Maclaurin series or something if you do the Taylor series at 0, but who really cares? Anyway, it's some type of Taylor series. So then you take the second derivative, you apply it at 0, you take x squared divided by 2 factorial, and then you keep repeating this kind of pattern. So in general, you take the kth derivative of f, evaluated at 0, take x to the k over k factorial. Is this familiar? Does this ring a bell? Or is this completely weird? Okay, good. But right, so this gives us a way to kind of write out, to say coefficient of x to the k, because it's, I mean, if you think about the Taylor expansion, that gives you a kind of, well, it's kind of an infinite polynomial, but it gives you a sort of polynomial where you have a coefficient of x to the k, right? So in that sense, for any kind of thing like this, I can ask you, what is the coefficient of x to the 10 for any p, which is not necessarily an integer. But in order to really understand this, we need to know what are these derivatives? Like, what do I put here for the kth derivative of f at 0? But that's just stuff you're used to, right? You can take derivatives and you can plug in 0. So, okay, so for the first one, f of 0 is just 1, right? It's 1 plus 0 to the p, p is not 0 and whatever. Actually, it wouldn't matter here if p was 0, so it's just 1. F prime of 0. So f prime of x is going to be p 1 plus x, p to the p minus 1. Plug in 0 I get p. Can anyone tell me what's double prime of 0? Right. Just take the derivative twice. That'll bring down a p. It'll bring down a p minus 1. And then you got the same stuff again, except with a p minus 2. And you plug in 0, and you get p times p minus 1. And in general, what you're going to get here is p times p minus 1, all the way down to, and it takes a bit of, you got to think about where does this thing end, but where it ends is p minus k plus 1, right? Because if I take the third derivative, it's going to give me like triple. So if I take triple prime of 0, it's going to, or, right? So this notation, so if I write f to the 3 in parentheses, that means the third derivative, right? So this is the kth derivative, and that's going to be p minus 1, p minus 2, right? So in general, you get p minus 1 all the way down to p minus k plus 1. So, right, so that tells us what to plug in this yellow circle here. So so it's going to be useful kind of for the analogy to the usual binomial theorem to think of this, to kind of define something to be like p choose k, where p is not necessarily an integer. So, right, so remember what this p and k is, right? The number of ways to permute, to take, you have a set of size n, you want to choose k of them and permute them, which was n factorial over n minus k factorial, or in other words, it's n times n minus 1 all the way down to n minus k plus 1. So we can define something similar for now if n is not an integer. So I'm going to define p, so I've got a big P of little p comma k. So a technicality, if k is 0, we make it 1. So p comma 0 is always 1. And if it's not 0, we define it to be p times p minus 1, p minus 2, dot, 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 down to p minus k plus 1. And so why are we doing this? Because, I mean, this is the same thing that appeared. This is the same thing that appeared before. This is our kth derivative applied at 0, right? This is the reason we're defining this. So what we've proved then is that f of x, so if f of x is equal to this for some p, then you can rewrite it as this using the Taylor expansion. And what we've said is that this is equal to, the numerator is equal to ppk by definition. That's how we define ppk. And define this ratio of ppk over k factorial, I define that to be, so this is if I write p choose k where p is not an integer, what I mean is this ppk over k factorial. So you can then write this as, maybe I'll, instead of writing f of x here, maybe I should write 1 plus x to the p. So the point is that 1 plus x to the p is equal to the sum k equals 0 to infinity of p choose k x to the k, where p choose k is this, and where this numerator thing was defined on the previous slide. Okay, but the way we derived this was just using Taylor expansion. Okay, is that all right? Okay, let's kind of get you to think about this to see if you do get what's going on here. So suppose, so I've included the definitions here because I know that these definitions are new for you. So if you take a look at these definitions, and I want you to compute negative 3 over 2 choose 2, which I admit is extremely weird because I've got a negative and a fraction in there. But yeah, the definition doesn't say p doesn't have to, has to be positive or anything, right? So this definition makes sense. So I mean, this is a valid thing to compute. So what is negative 3/2 choose 2 according to these formulas? Maybe no one's answering because they don't know I haven't started the Jeopardy music. Okay, I'm getting a few answers. So the first thing to try to compute, right, is what is p negative 3/2 2? And then you want to divide that by, well, maybe I can write the whole thing. So it's going to be this, right? So negative 3/2 choose 2 is equal to this, just by the formula on the left side. So 2 factorial is just 2. That's easy. What's negative 3 choose, or sorry, p negative 3 over 2 comma 2? It's negative 3 over 2 times negative 3 over 2 minus 1. And if you think about it, so this is, so this thing is negative 5 over 2. You multiply these things, you get 15 over 2, or sorry, over 4. And then you have another 2 here, so it's 15 over 8. Okay, so weirdly enough, you can take negative 3 choose 2, which, I mean, the combinatorial understanding of n choose 2 is like choose 2 things from n things, which doesn't make sense here because you can't choose 2 things from negative 3 over 2 things. But the definition, formally, it does sort of make sense in this context at least. Okay, so this is what we've proved by using the Taylor expansion, is that for any p that's not 0, 1 plus x to the p is equal to the sum of p choose k x to the k, which is an extension of the usual binomial theorem. So the only thing that looks different, I think, here, like, so if I just plug in n equals p, right? If I plug in an n here, right, I plug in an n here, you basically get the usual binomial theorem. The only thing that looks weird is this infinity, right? Because if I plug in n, usually the sum goes from k equals 0 up to n, not k equals 0 to infinity. But the point is that if you plug in p equals n, then actually when k is bigger than n, n choose k is 0, right? I can't choose more than k n things from n things. So the point is that if I take n choose k, where k, so it's 0, k is bigger than n. So actually you can write this, the usual binomial theorem, as an infinite sum because, practically all the terms are just 0. And if you add 0 to itself, or you add 0 to something infinitely many times, it doesn't really matter, right? It stays the same. Okay, so that's kind of what is being explained here. So this is like an extension of the usual binomial theorem to cases where the exponent is not an integer. Okay, so what I'm going to do in the rest of the time is show you a cool application of the binomial, this Newton's binomial theorem, it's called, to determining the generating function of a kind of complicated looking sequence. Well, the sequence looks simple, but the generating function is going to be a little bit weird, but we're going to show that it comes out from this binomial theorem. So I want to find the generating function for the sequence an equals 2 to the n choose n. Okay, so in other words, I've got the sequence, 2 times 0 choose 0, 2 times 1 choose 1, and so on. And I want to show that the generating function for the sequence is this weird looking thing, which is 1 over the square root of 1 minus 4x, which is not really the form, like we're really good at dealing with things that look like this, right? This is our bread and butter, right? We're really good at dealing with that. We're less good at like dealing with things that have square roots. So what I want to do is show how you can use this binomial theorem, this Newton's binomial theorem, to get the coefficient of x to the n in this thing, and we're going to show that it's equal to 2n choose n, which is kind of a cool application. So in other words, we want to show that if I take the sum, let's say k equals 0 to infinity, so I'm kind of changing my variables a little bit, but it doesn't make a difference, right? If I take 2k choose k x to the k, I want to show that this is equal to 1 over root 1 minus 4x. So this is the statement we're trying to prove. Is that clear? So this is what we're trying to prove. Let's look at the right-hand side. So let's look at this weird square root thing. So if I take this 1 over square root of 1 minus 4x, I mean, obviously this is just equal to this, right? So 1 over a square root is just like taking an exponent of negative a half. So that's cool. I can deal with that. And now if I do a substitution where I substitute y equals negative 4x, then this is just 1 plus y to the negative a half. So in terms of y, we can kind of, we can apply this Newton binomial theorem. So, okay, so if I expand this using that binomial theorem, I'm going to get something like y to the So the kth term is going to be like something times y to the k, right? Where that something, so remember 1 plus x to the p is the sum k equals 0 to infinity of p choose k x to the k. And here my p is just negative a half choose k. So, okay. Which, okay, this is great, but I'm not that enthusiastic about y. Like, I wanted this in terms of x. But we can just do our substitution again, right? So y is negative 4x, and I can just plug that in. So I get negative a half choose k, negative 4x to the k, which is the sum k equals 0 to infinity, negative a half choose k, negative 1 to the k, I'm going to call my 4 2 to the 2. Okay, so it's 2 to the 2k x to the k. Not that it really matters. Okay, so this is the right-hand side of this equation. Now I'm going to keep playing with this and try to show that it equals the left-hand side. Now, all of these pieces are kind of okay, except for this one. Like, I mean, even this is okay, but we have to kind of understand what is this. Okay, and then if we can understand what that is and we can plug it in, then some things are going to cancel, and hopefully we'll get to here the index is k, so hopefully I'll get 2k choose k after we figure out what this is and we substitute it back in. So with regards to the question of what is negative a half choose k, so what I want to show, I claim that it's equal to, so above this line is the thing I'm claiming, and below the line is the proof. So I claim that it's equal to negative 1 to the k, 2k choose k, over 2 to the 2k. And the proof is basically just to, use the formula and manipulate it. So negative 1 choose k is, so if I wanted to insert a kind of middle step here, I can say negative a half choose k is p negative a half k over k factorial, right? Where p negative a half k is just equal to what's on the top here. So it's negative a half times negative a half minus 1, negative a half minus 2, to negative a half minus k plus 1. And then I've got this k factorial on the bottom. Now this is kind of an exercise in how good are you at fractions. But okay, what is negative a half? Well, that's negative a half. What's negative a half minus 1? Negative a half minus 1 is, it's like negative 1 on the top minus another 2 on the top over 2. Right, because this 1, when you put it on the top, if you do the fraction thing, it's like that. Then you have negative 1, so you have negative a half minus 2, which is negative 1 minus 4 over 2, if that makes sense, and and if you think about it, the last term is going to be negative 1 minus 2k plus 2 over 2. So what I'm doing here is just rewriting this product. And now you see that you got a whole bunch of 2's on the bottom. And I can kind of pull these to the bottom of the entire fraction. So I've got, on the top I've got negative 1 minus 2, negative 1 minus 4, down to negative 1 minus 2k plus 2. And on the bottom I've got 2 to the k, which is from these 2's, times k factorial. Now, I can also pull out all these negatives, because I don't like negative numbers, right? So it's much easier to deal with positive numbers. So I pull out all these negatives and I get a negative 1 to the k. If you think about what I've got here, is I've got negative 1 to the k over 2 to the k factorial, times the product of all the odd numbers, 1, 3, 5, up to 2k minus 1. I've got all the odd numbers, which is weird. But if you think about it, if I've got all the odd numbers from multiplied from 1 to 2k minus 1, that's kind of the same thing as multiplying by all the numbers, 1 up to 2k, and then dividing by the even numbers to cancel them. So in other words, this is all just bookkeeping, right? It's just like, can you manipulate the algebra? It's a little bit hard to convince you of every step over slides, but yeah, so, okay, what is the product of all the odd numbers from 1 up to 2k minus 1? Well, it's kind of like 2k factorial, except that all the even I shouldn't say terms, I should say factors here. All the even factors are missing. So that's the same thing as taking 2k factorial over 2 times 4 times 6 up to 2k. But now on the bottom here, I can factor out 2 from every term. And what I get is 2k factorial here over 2 to the k factorial by pulling out a 2 from all these even numbers. Now plug this in, and what you get is that negative a half choose k is negative 1 to the k, 2k factorial over 2 to the 2k, because there was a 2 to the k before, and I've got an extra one here, times k factorial. One of them is from here, and one of them was on the previous slide. And long story short, it's equal to negative 1 to the k over 2 to the 2k times 2k choose k. Okay, that's a lot of algebra. I think each individual step is not too hard, but unfortunately there was a lot of steps. But now I plug this back in. So I plug it in where? Here in this green box. We now have a formula for this thing here, this negative half choose k. I plug in the formula for it, and basically everything cancels. So just yeah, it's hard to, if I plug in here, yeah, the negatives go away because I've got negative 1 to the k here. This is not going to work. And I had a negative 1 to the k here, so that becomes negative 1 to the 2k, which is 1. The 2 to the 2k's cancel, and what you're left with is just this remaining thing, which is this 2k choose k. So if you do the algebra and you plug things in, you'll see that that's the only thing that remains. So yeah, so that's the answer. So that's the end of the proof.